Okay, we are going to build on the characteristics that we've already talked about with functions and talk about some more characteristics. And so we're going to start by, I'm going to give you a function, we're going to graph it, and then I'm going to bring up all sorts of different questions I could ask about it. So the function that we are going to talk about is f of x is equal to 1/2 x minus 1 squared minus 2. So when I go to graph this, and I'm going to keep showing you my kind of shortcut method, I think that it will help you in the long run get it. But really quick before I do that, I'm also going to show you a table method because if you remember, I don't mind which method you use, you just need to be efficient at the method that you choose. So -2, -1, 0, 1, and 2, and this is the parent function x squared. So 4, 1, 0, 1, and 4. Now, if I want to talk about transformations, I know that what's happening inside my function, so inside of the squared, will affect the x values of my transform function. And so we know that in the form y equals a times x minus h squared plus k, h is your horizontal shift. So in this case, x minus 1 is a horizontal shift, right 1, which adds 1 to each of my x values. And then a is either or is both a reflection across the x-axis if it's negative, and it's your vertical stretch or compression factor. So in this case, 1/2 is going to compress the function. So it's almost like I'm holding the top and the bottom of the function and smushing it. So it's going to make the function wider than the parent function. And it is shifting it down too, because k is my vertical shift down 2. So then I can apply these transformations to the points on my original table. So -2 plus 1 is -1, -1 plus 1 is 0, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3. And then I'm going to take the y values, I'm going to multiply them by 1/2 and then subtract 2. So 1/2 times 4 is 2, minus 2 is 0. 1/2 minus 2 is -1.5. Let's see where we're at. 0 minus 2 is -2. 1 minus, or times 1/2 is 1/2 minus 2 is -1.5, and hopefully you're seeing that symmetry. And then 4 times 1/2 is 2, minus 2 is again 0. So you can plot these 5 points by getting them in this form, or you could have recognized, maybe I'll do it in a different color when I actually graph it. You could recognize that the vertex is 1, -2. I know the function opens up because it has a positive a value. So there's not a reflection in the x-axis in this case. Had it been -1/2, then it would be reflected over the x-axis. But it is compressed. So for a quadratic function, usually I would go over 1 from the vertex, up 1 squared, but I'm going to compress that by a factor of 1/2. And I graphed that backwards, didn't I? So I'm sorry, 1 -2 would have been here. Sorry about that, guys. So then over 1 from the vertex, up 1 squared times 1/2. Make it symmetric. Over 2, up 2 squared, and then compress that by a factor of 1/2. Over 2, make it symmetric. And those are those 5 points that we just had right here. Same exact points. If you want to put one more on here just for fun, 1, 2, 3, I should go up 9 for the parent function, but I'm only going to go up half of that because it's compressed. 1, 2, 3, 4.5. Then we'll make that symmetric. Look at that beautiful parabola. Not a point. There we go. All right, so now let's talk about some of the characteristics of this. Obviously, we know the vertex is the point 1, -2. And this point is a relative minimum because it's the lowest point in that area. But if I asked you what is the minimum value of the function, that's the y value of the function. So the lowest, so that's the output. So that would be -2. The next thing I want to talk about are something called zeros. Zeros are the values of x for which the y value is 0. So the zeros are at what x values does y equal 0? So now you kind of have two options. One option, you can actually plug in 0 for y and solve. And the other one, you can take them from the graph. So obviously, I hope that you would just take them from the graph in this case. But after looking over your last quadratics worksheet, I actually want to solve this because I want to, there was a consistent issue, and I want to try and fix that issue. So when I solve this, I'm going to use square roots. So I'm going to add 2, and then I want to get rid of that 1/2. So to undo the 1/2 times x minus 1 squared, I could divide by 1/2, or think about what I would need to multiply 1/2 by, so that it becomes 1. So 1/2 times 2 is 1. So I'm going to think of it as multiplying by the reciprocal on both sides. So then I have 4 equals x minus 1 squared. Take the square root. And then 1 plus 2 is 3. 1 minus 2 is -1. So obviously this was not necessary, but I just wanted to walk through solving that with you one time. Now, the zeros, at this point, when we talk about zeros, we know that our zeros are going to be our x-intercepts. Eventually, we will talk about how to find zeros that aren't x-intercepts and what that really means. But that's something that's like chapter 2, maybe chapter 3, and we're not there yet. But our x-intercepts are the coordinate pairs. So the zeros are almost like a solution to an equation, whereas the x-intercept is a specific location on the graph. So if something's a specific location on the graph, it's a coordinate pair, it has an x value and a y value. Notation is very important between these two, and I notice that, or I hope that you notice that they are very similar, but it is something that I will look for in your work and make sure that you understand. All right, the y-intercept is on the function, so it's just 0, -1.5. You also could plug in 0 for the x value and evaluate and find the y value. Find the y value. Let's talk about domain and range. Domain is all of the possible x values that are used in the function. So we know it extends indefinitely to the left and to the right. We know to the left on the x-axis is -infinity, and on the right is infinity. So one option using interval notation would be -infinity to infinity. Another is you could say all real numbers, which you could actually write out, or there's this fancy R that is sometimes used, and either of those would be acceptable. The range is all of the y values. So we always read bottom to top. The lowest y value is -2. And -2 is a y value. So I'm using a bracket to show that -2 is included in the range, and it goes up to infinity. Another way of saying this is y is greater than or equal to -2. Those are the same thing, it's just two different options. Next, I want you to find f of -2. Well, we have two options. You can plug -2 into the function and get the output, or we can come over here to -2 and see what the y value was. So that was at 2.5. So f of -2, this is saying when x is -2, what does the y equal? It was 2.5. All right. The next one I want to answer is, I'm kind of scrolling a lot. Let's see if I can. Let's say I want to find, I'm going to erase these tables so I have more space. Let's say I want to find the values of x when f of x is equal to -1.5. So again, you could set y equal to -1.5 and solve the equation in this case, or we could come up to our graph and look when y is -1.5, and that would be at x equals 0 and x equals 2. You could solve it algebraically, or you could solve using the graph. Now, the one time you wouldn't be able to solve using the graph is if it didn't hit at a nice value. We know that those 2 points, it hits at a nice value because we graph those points. Otherwise, you would have to solve. So an instance like that, when it doesn't hit nicely, find the values of x when f of x is equal to 12. So in this case, we don't have those points graphed on our function. We don't have a nice way to solve. So I actually have to solve. So my function f of x is 1/2 x minus 1 quantity squared minus 2, and I'm going to set that equal to 12. And then I'm going to solve. First, I'm going to add 2. And then I'm going to multiply both sides by 2 to eliminate the fraction. Take the square root. Simplify this radical. If I'm looking for a perfect square that goes into 28, 4 comes to mind. So then x minus 1 equals plus or minus 2 radical 7, and then add 1. So the values of x when f of x is equal to 12 are 1 plus or minus 2 radical 7. All right, let's go back up to the graph. A completely new, I believe, concept for you is something called end behavior. So end behavior, when we describe end behavior, it answers 2 questions. So as x goes towards infinity, what happens to the y values? And as x goes towards negative infinity, what happens to the y values? And so what we are answering is basically telling where the ends of the graph are going. So as x goes to infinity, that's talking about the right side, because the right side is going to, or as x gets really big, where's the y's going? And then that would be going up towards infinity. And then let's do a different color. As x goes towards negative infinity, so as x gets smaller, where are the y's going? And that's also going towards infinity. It should make sense that for a parabola, those are always going to be the same because of the idea of symmetry and the shape of the parabolas. So those will always match. So they will either be infinity or negative infinity. Next, I want to talk about the intervals of x for which f of x is increasing, decreasing, positive, and negative. So for these 4, this is what we talked about in the last video. Increasing, if you think about this kind of like a roller coaster, increasing would be going uphill if you were driving along the function, remembering that we always drive left to right. just like we read, just like we graph. We don't always drive left to right. Just like we graph is what I meant to say. So increasing, as I am reading the graph left to right, if I'm imagining I'm on a roller coaster, I am going downhill. So my height on my roller coaster is decreasing until I get to the vertex. So at the vertex is where I stop decreasing. So from negative infinity, remember I'm giving an x value, negative infinity until 1, my function is decreasing. From 1 until infinity, my function is increasing. So as I am considering decreasing and increasing, I am keeping in mind my vertex. The next question asks me positive and negative. And for some reason, I think about like above ground and below ground. And I know that ground level, when the height is 0, is the x-axis, which if you think about, those are called zeros. So above ground is positive, below ground is negative. So I want the intervals for which my function is above ground or positive. So that is this part of the graph and this part of the graph. So that is from the x value of negative infinity until I get to an x value of negative 1. So until I get here. And then again, so this union, remember, means or in math, from 3 until positive infinity. And remember, you're giving me an x value. So these are all x values. And then negative, so negative is when a function is below the x-axis, when it's below ground. So that would be from negative 1 to 3. That is this part of the graph. All right, I want to do one more thing with this function, and I want to write it in standard form. You have done this before, but I want to just practice it some more. So we have 1/2 x minus 1 squared, which we know means x minus 1 times x minus 1, and then minus 2. So the first thing I will do is FOIL x minus 1 and x minus 1, which is x squared minus x, so 2x plus 1 minus 2. And then I'm going to distribute my negative. And then I'm going to combine like terms. 1/2 minus 2 is negative 1/2, or negative 3 over 2. And there's my function. All right, that was a whole lot of information, but you can, a lot of that wasn't new, hopefully, and you actually did a lot of these concepts in Algebra 1 a couple years ago. So hopefully it doesn't seem overly hard, but it is just a lot of information. It's a lot to analyze all at the same time. So I want you to try some on your own for homework tonight, and then we will do another example in the Google Meet either Monday or Tuesday, depending when I'm seeing you. Thank you so much. Have a nice day.